Hello everyone, welcome. Today we'll learn about continuity. So our goal is understanding the meaning, what it means for a function to be continuous. We'll determine whether or not a function is continuous, have some ways of doing that, and also understand different types of continuities, practice of continuity, and also understand what's called the intermediate value, and a few other topics. So first, let's talk about continuity, what it means. It's something you've probably heard of before, but may never had a visual definition. So a continuous function, as it says, a function with basically no holes or gaps. Okay, you can draw the function. The easiest way to say is you can draw a function, continuous function without ever lifting your pencil. Okay, so let's come over here. So a continuous function would be something like anything like this. Okay, because basically I was able to draw that without ever picking up my pen in this case. Okay, so this is continuous. Now, examples of non-continuous, and actually kind of three generally different things can happen from non-continuous. Okay, so let's draw a similar one to this, except let's say it has a hole in the ground. So this example is something that's not continuous. I just say not, okay? Has a hole in the graph there. Or what if you have another function? These are all still functions. Maybe a function looks like this, where in this case, there's no function was defined at all at this point. It could be or not, but basically there's a hole in the graph right here. In this case, there's actually a separation between one part of the function and the other, okay? This is also not continuous. And also any place you have an asymptote like this. Let's say you have a vertical asymptote that looks like a function looks like this. And we've seen, if you learn about rational functions, you've seen functions like this before. This is also not continuous. And these particular functions have common names too. So let's actually jump in here briefly for actually the definition of a function and talk about types of discontinuities. The first one is something called a removable discontinuity. And it's sort of called that because basically when you have a hole in the graph, it's called a removable discontinuity. So basically you just essentially define the function. If the function is defined somewhere else, like there's a dot up here, maybe you could just simply define the function to exist right here, then it wouldn't be continuous. That's what makes it removable. So it's kind of a way of kind of removable in the sense remove the discontinuity. So if I replace that with a hole with a dot there, it makes the function continuous. If I can do that by just replacing one point, then basically it means it's a removable discontinuity. Okay. Now, the one in the middle is something called a jump. And actually, these are called discontinuities. I'll just abbreviate that, discontinuities. Okay. The second one's called a jump discontinuity. Okay. Because basically the functions come to an end right here, the parts of it, and basically get from one to the other. You just have to jump down to this one or jump up to this one to continue. Okay. That's what's called a jump discontinuity. And then finally, this one is called an infinite. I'll abbreviate that discontinuity because you have a vertical asymptote. Okay. It's basically different from a jump discontinuity. And this one, we're always going up forever from left to right. So you can't really jump from one to the other because you never cross this line. Your function never cross the line. So that's what's called an infinite discontinuity. So those are the main types. Now, what makes these things continuous and not continuous? Well, basically, let's learn the definition of a continuous function at a point. A function f is continuous at some point a if as limit as x goes to a, if f of x equals the function value there. Okay. So if this is our point a, let's actually work with all three of these. If this is our point a right here, okay. So imagine this being like an x-axis. This is a, and this is a right here, where this happens. Okay, so why isn't this one continuous based on the definition? Well, true that the limit as x goes to a of f of x exists. Okay, both the left and right limits go to the same point. But does not equal f of a because In this case, since either f of a isn't defined or f of a is another point. Since in this case, f of a, there is no f of a, so we can say f of a does not exist. Okay, there is no f of a in this case. Or if f of a was another point, then maybe a dot above or below. And also basically to be able to be continuous, the limit has to be the same as the function value. In this case, there's no function value right there. Okay. Now, what about this one? Let's actually, you're all line, you have a little separation. I'll go over the jump discontinuity. Well, in this case, your one side limits don't exist. So actually, an f of a exists right here, this dot. But in this case, why is it not continuous? Because the limit as x goes to a from the right of f of x is not equal to the limit from the left. So remember, to be continuous or to be or for the limit to exist at a point, your left and right limits have to agree, have to be equal. Okay. Since those are not equal, then this function is not continuous since they go to different things, even though the function is defined. Okay. And in a sense, this is also out of place. And also, anytime you have an asymptote, basically the limits here go to infinity or negative infinity. And basically, also remember here, the function can't cross that value. The function can't cross vertical asymptote. Okay. And basically, in this case, anytime you have asymptote, the function can't be continuous anyway. Okay, so basically it fails that because the limits don't, in this case, the limits go to infinity and negative infinity. But if they both went to infinity or both went to negative infinity, it still would be continuous. Okay, so that's the idea of continuous and how it can essentially continuity can be broken in a sense, how a function can be discontinuous. So over here, to determine whether a function is continuous or not, we have what's called, I took this cited from textbook, called a continuity checklist. It's a good way of thinking about it. So basically, that takes this apart. So if the function is f is continuous at some point x equals a at some value, then these three following things must be true. F of a has got to be defined there. Okay, as a is part of the domain. So like in our first example here, that wasn't true here. The limit of f of x exists, though both left and right limits have to agree, as they do here. And basically, then the third thing is that that limit that exists has to equal the function value at that point. Okay, so let's go right below and look at a quick example right here. Okay, so let's just make another function value. Let's say here is our a, and our, so this is our point x equals a, and let's call our y value L. A lot of times L is used for this for different reasons. Okay, now let's check these things. Okay, so from our checklist, okay, so f of a defined, okay, that checks. Okay, we have a value here at f of a. All right, the limit as x goes to a of f of x exists. Okay, so it's not going to infinity or negative infinity. Basically, both come to the same point. Okay, you see that checks, and then that limit as x goes to a of f of x equals f of a, that checks. So it's continuous. This function is continuous at x equals a. Okay. So that's the basic idea of continuing. Also, how we kind of show something is continuous, how it can not be continuous. Now, a couple rules about functions in general. So a nice thing is if two functions are continuous to begin with, then usually in various ways we combine them, the result will also be continuous. Let's look at this over on the left as continuity rules. So if functions f and g are continuous at some point x equals a, then these following combinations of functions are also continuous at the same point. Okay, so if we add the functions, f plus g, f minus g, if we have c as a constant, so c times the function f, c times, so basically let's back up. The sum of two continuous functions is continuous. The difference or subtraction of two continuous functions is continuous. A constant times a continuous function is continuous. Two continuous functions multiplied together is also continuous. And two continuous functions divided is continuous as long as we're not talking about a place where the bottom function g is 0. Then also a function to a power n where n is an integer is also continuous. Some other nice things. Polynomial functions are nice. And basic polynomial functions are continuous for everywhere, for all values of x. And it's also true of rational functions, where the rational functions have a function made up of a polynomial divided by another polynomial. And basically they're continuous except for the points where the denominator is equal to 0. Okay. So let's take a look at a few more examples of this and practice with these ideas. So let's take a look at this graph. And let me actually enlarge it a bit. Okay. I also have another graph down here. We'll take that one here in a moment if we need to. Let's take a look at this graph, look at some examples we have. Okay. In this case, we actually have the specific numbers. So let's take a look at x equals 2. Okay. So at the point at x equals 2, all right, this is what's happened. Okay. So if we look at the limits and think about our checklist again, let's go back to our continuity checklist. Okay. So let's ask this question. So is f continuous, okay, at x equals 2? Let's take a look. So at x equals 2, all right, so f of a does exist. F of 2 is equal to 3. Okay, so it does exist in this case. That's true. The limit as x goes to 2 of f of x. Think about the left and right limits here. Okay, we clearly see they're both going to 1. Okay, that limit equals 1. Okay, if they're both going to 1. So clearly that's also a check. Move this down just a bit. Let's move that to the next page. Okay, but so that checks. But as you can see, the problem we have is that the last part is the limit as x goes to 2 of f of x is not equal f of 2. To plug into, we said it's defined to be 3. Okay, but our limit is equal to 2, so of course our limit is equal to 1, so of course 1's not equal to 3, and so this one is not continuous at that point. So not continuous at x equals 2. Okay. Now let's think about x equals 3. Okay. So at the point, so look better. This time at x equals 3. All right. So once again, the same question, is the function, is f continuous at that point? So let's go think about our checklist again. So first off, is f of 3 defined? And it is. Okay. If we look, f of 3 is actually 1. So it's defined there. We'll call it solid dot. Okay, if you notice, these are both filled in, it would no longer be a function at that point. Okay. Now, what about the limits? Here's where you could have an issue. So the limit as x goes to 3 from the right, so coming from the right, okay, going toward here, is actually equal to 1. And the limit as x goes to 3 from the left, this time coming from this direction, it actually goes to 2. So that's from the left. So, of course, 1 is not equal to 2. So, not continuous at x equals 3. Now, we see some places where the function is continuous. Now, I don't tell what the values are, but right here, for example, this point right here, it's like x is maybe about, I don't know, maybe 1.5. It's definitely continuous there. But this particular place is not continuous, okay? And also this is called a removable discontinuity, because if I just define the function if I just defined or changed my mind, made f of x or f of 2 equal to 1, it would be continuous there. This one is a jump discontinuity, okay? Because basically they're separated by a section. And when x is equal to 5, that's where you have this other discontinuity. Just draw a line, and we'll take a look at that one. This time, let's look at x equals 5. So once again, is our function f continuous at that point? If I can clearly say it's not, let's kind of explain why. Okay. So basically here, f, I guess the simplest answer is f of 5 is not defined. Okay, because there's an asymptote, a vertical asymptote at that point. So anytime you have a vertical asymptote, that means the function is not defined, means you're dividing by 0. Okay, we have a vertical asymptote. Okay, so basically what's happening here is that 5 x equals 5 makes our function, makes f of x equal to 0, or makes f not equal to 0, makes fx undefined. Okay. All right. So that's the idea of graphical atomic continuity. Let's see. So next, let's actually look at a specific function. So actually, let me move this down a bit more. I'll actually use this part here for another graph. Let's do another example. Let's do an actual where you instead of giving a graph, I give you a function. Okay, so another example. Let's call this number 1. So let's do f of x is equal to x squared minus 3x minus 10 divided by x squared plus 2x. Okay. Now, once again, let's actually go to Desmos and graph this first. It's always a good place to start. And that will give us some ideas. Because remember, no matter what happens, wherever our denominator is going to be 0, we know we have something, either hole in the graph or a vertical asymptote. Let's see what happens. All right, so remember, if I want to do a fractional function, put the number in parentheses, x squared minus 3x minus 10, then divided by x squared plus 2x. Okay, so it looks like we have one vertical asymptote. It's like close to 0. All right. Now, the way we can be certain about that, be sure about that, is what we need to do then is go back and let's actually find the exact value. Let's actually factor. All right. So in one case, if we can factor, let's factor this. And this one, both numerator and denominator have factors. So it factors into x minus 5, x plus 2. And then we factor the denominator. Factors into x and x plus 2. Okay, so what we can see is, of course, that x can't be 0 and x can't be negative 2. Now, as long as that's the case, I can actually cancel these out. And this is equal to x minus 5 over x when, as long as x is not equal to 0, x is not equal to negative 2. Okay, think of it like that. All right, so that's where I have a vertical asymptote right there. Okay, so if let's do just a kind of really quick picture of that function. Let's go back and take a quick look at it, make sure I remember which way it goes. Okay, like that. Okay, so this function looks kind of like this. All right, so right here at and vertical asymptote at x equals 0. Now we also have when x is equal to 5, we have a little hole in the graph right here. Okay, so we did an asymptote, or I'm sorry, an x equals 2. Let me just change that real quickly. So x equals 2. Okay, in fact, I may need to go back and draw that better. Let's go back and take a look. Yeah, actually, I should, because actually the x values are crosses. So let me change this up just a bit. All right. Actually, let's make this 5. That's where the 0 is. It's across the x-axis. Let's say right here, you have a bit of hole in the graph where x is equal to 2. It looks something kind of like this. You have a hole in the graph right there. It should cross at 5. Okay, so that's what this function looks like. All right, so here we have two discontinuities. Okay, so it's discontinuous at, of course, x equals 0, a vertical asymptote there, and also at x equals 2. That's a replaceable discontinuity because basically it's not defined there. Okay, because of x is equal to 0. So it's discontinuous at both places. And actually, if we go back to Desmos, should be able to see that. Okay, if we go up to 2, when x is equal to 2 right here, if I just get it just right. Actually, that's not. Oh, -2. Right. There it is. I'm sorry, I got that wrong. -2. So I actually need to go back and correct that. Sorry about that. Actually, my hole in the graph should be over here. Sorry, -2. Should have been more careful. The hole in the graph is actually right there. Okay, so discontinuity is there. We have the replacement discontinuity right here, then also right here. We have a infinite discontinuity because we have an asymptote. Okay, now let's talk about the next concept we're going to talk about is continuity on an interval. Okay, so an interval of a function is basically some part of a function. And most times, real life, we work with functions, especially a lot of like polynomial functions. Often you're not looking at the entire thing everywhere. Often we're rarely does ever interval ever go from infinity to negative infinity to real life. Um, Often we have to just take a part of a function. So we have to think about an interval. Okay. Continuity on an interval. So the idea, if I have some function, let's just do a really basic function right here. Okay, let's just put this as this is A and this is B. Okay. And actually, let me do a function where it's easier to distinguish A and B. So in just a second. Yeah, that's better. Makes it easier to separate A and B. So here is, of course, f of A. And then here is f of B. Okay. Now, so on an interval A to B, okay, so we're just talking about this part of the function right here. Okay, it may go on forever in both directions, but what we care about is interval, you know, here, A and B. All right, which may or may not include the endpoints, depending on what kind of situation we're looking at. Okay, so function is continuous on an interval if it's continuous at every point in the interval. Okay, and therefore contains the endpoints. The function is continuous from the left, the right of those endpoints. So what does that mean? Well, if we think about a closed interval right here, okay. In fact, let me just redraw this picture. Let's just take a look specifically just at this interval. Let me move this out of the way. Let me go back up here. Let's look just at this function on the interval. All right, so draw a very similar picture. I try to draw basically the same picture. Let's say you have this function looks like this. Okay, so once again, this is A, this is B, and this is f of A, and this is f of B. Now, if we're talking about the entire interval, including the endpoint, so what we have to think about then is we talk about what's called the limit function is continuous from the right at A. Okay, so at A, if you notice here, there's nothing on this side. Okay, right now we're only thinking about just this interval. Okay, we don't care if the rest of the function exists or is there. So here, of course, I can't approach f of A from the left. I can only approach f of A from the right. Okay, what this says, this idea of continuous from the right at x of A, if the limit of x of A from the right is equal to f of A. Okay, they can clearly say that's true. Okay, so the limit of as x goes to A from the right of f of x is equal to f of A. See that from the graph, I go in this direction, go down there toward A from the right. That's the same as f of A. Okay, but then the limit as x goes to A from the left of f of x. Notice I can't come from this direction because the function doesn't exist there. So this does not exist. But that's okay. That doesn't really affect what's going on with this. Okay, that's all right. Now, in the same way, think about the limit going toward B, the limit as x goes toward B from the left, because it has to be where the function is defined of f of x. Okay, and is that the same as f of B? It is. So if we come from the left toward B, turns out this function that's the same as f of B. But if we try and think about the limit as x goes to B from the right, once again, we can't do that because it's not defined there. So we'd say that does not exist. Okay. So since both those exist, so what we can say then is that f of x is continuous on the closed interval a to b, since is continuous from the right at a and from the left at b. So as long as the limits within our function, within where our function exists, as long as we approach the endpoints within where our function exists, and the endpoints are actually the same as the function, then we can say that's continuous on the interval. Okay, so let's use this graph here to explain, to kind of explore some of those ideas. So first off, let me enlarge it a bit and look at some of these ideas here. Okay. I'm going to draw a line to separate these. Let's look at this graph. This is our function f of x. Okay. Now, as we've seen already, we got a few things already. Okay. So for example, this point right here at 1, we tell the function is continuous there because it fits our checklist. It's defined there, and our limit's equal to that. We have a infinite discontinuity right here at 3, means the function is undefined there, so divide the function by 0 at 3. Then we have a couple of the jump discontinuities here and here. Okay, but now in this case, it's actually thinking about this idea of continuity on an interval. Okay, so f is continuous on the following intervals. All right, so first off, let's take a look over here. All right, so clearly we can see that everywhere, if we don't include 0 or 2, everywhere between 0 and 2 in terms of x, it's continuous there. Okay, we don't have to pick up our pencil or pen to draw it there. Okay. Now, what about our endpoints? Well, this one, if we approach this one is defined there. That's f of b. And also as we approach that one from the right, approach the right endpoint, sorry, approach the left endpoint from the right, from the left, it's the same as the function value. So that's true. So this goes from continuous on from 0 to 1. Actually, put it down here. So consider 0 to 1. At 1, it's continuous. The endpoint's included because the endpoint value is the same as the function limit, okay, from the left. What about from the right? With this one, the limit as we go to this endpoint from the left, or from the right rather, is equal to 2, but the function is not defined there. It's an open hole. Okay, so in that case, we can only put parenthesis there because that function point is not defined there. Okay. Now, what about the other places where it's continuous? Well, this part here is continuous. I actually have 3 more parts continuous here, here, and here. Let's talk about each one. Okay, this one starts at 2. Remember, you separate these with the union symbol. So this time we go from 2 and then to 3, remember, in terms of x. Okay. In the same way, this point's not included, and the limit, although the limit goes to this point, limit goes here to 5. This point's not included. That's a parenthesis. Of course, anytime you have a vertical asymptote, it's also not included. So this case is continuous from 2 to 3. Over here, another union symbol, it goes from 3 to 5, 3 to 4 rather. Okay. In the same way, a vertical asymptote is not included there. And here, once again, the limit as x goes to 4 is equal to 5, but the function value is not defined there. It's defined down here. Okay, these are not equal. And so that one's not included. And then the last one, from 4 to 5. And once again, we just said this one's not included because the limit and the function value are not the same on the endpoint. Use parentheses there. And here, once again, the function value is not defined. Use parentheses there. Okay. So if the function is, if the endpoint value is defined and the function limits to that from within where the function exists, like this case from the left, then we can include the endpoint. If not, we don't. That's the idea of continuity on an interval. Okay. Let's talk about another example. So let's do a different type of problem. So let's call this 1 again. Let's say we have this function. So f of x is equal to the square root of 25 minus x squared. Okay, so 25 minus x squared. What I want to find out is kind of take a look at this function, also see where it's continuous. So where is it continuous? That's our question. And based on what intervals is it continuous, or where is it continuous? Okay, so once again, first, let's graph it. That's going to help us to get an idea of what to expect. Okay, so let's go back to Desmos. All right, so I'm just going to turn this one off. We're going to come back to it at some point. Let's go down here to number 2, and then we're going to do square root. You can either do the square root down here, so on the keyboard, there's a square root button. It's easier just to type in SQRT. Okay, then do 25, make sure within the square root, minus x squared. Oops. Okay, let's actually get rid of that, and that's what we have. Actually, what we have is the upper half of a circle with a radius of 5. Okay, so that's what our function looks like. Now, what it looks like is based obviously continuous all the way from -5 to +5. Then we have to think about whether the endpoints are included or not. Okay, that's where it's continuous. Let's think about that. So how can we figure that out? So what we say right now is it looks like continuous from -5 to 5, probably with endpoints included. Let's talk about that. Let's do a very, right down here, I guess. Let's do kind of a basic graph of that. Okay. Now let's think about the endpoints. So one way to figure out the endpoints help us out here at 5 and -5. And let's think about this. So our function, where it's going to be defined, well, remember, since we're taking the square root, Also, a couple more things. So let's go back to our rules up here. And let me back for a second. Let's see. No, let's not do it that way. Let's think. Okay. It turns out that actually, since this essentially 25 minus x squared is a polynomial, that's continuous everywhere. Okay. But here, since we have a square root, we have to think about where is, make sure this has got to be positive or zero. Okay. So to be real, real mean not imaginary, 25 minus x squared has got to be greater than or equal to zero. So let's actually solve that. Help us understand a bit better. And so first let's subtract 25 from both sides. So we have negative x squared is greater than or equal to negative 25. Let's divide both sides by negative 1. And that's going to make this x squared a positive 25. Remember, if you divide or multiply both sides by negative, you switch your signs. As x squared is less than 25. And technically, if you take the square root of that, then actually this makes this technically the square root of the absolute value of x is less than or equal to square root of 25, which of course is 5. Okay, and that's what we can see in the graph. Now, clearly it's continuous between negative 5 and 5. Okay, possibly not including those values, but there's between those two. Okay, so that would be negative 5 to 5. Okay, but then we want to say, what about the endpoints? Okay, well, let's plug those in the function. So f, let's plug in the first, it doesn't matter, x equals negative 5. And so that's going to be f of negative 5 is going to be the square root of 25 minus negative 5 squared. You square negative, you get a positive, and so that's going to be square root of 25 minus 25, which is the square root of 0, which is 0. So that's okay, right? Now, so the endpoint is 0, okay? Now, let's take a look back at our graph. So in this case, if we approach this within our where our function is, we have to approach this from the right, okay? So let's say this. So f of negative 5 is equal to 0. Okay, so the question next is the limit as x goes to negative 5 from the right of f of x equal to 0. Instead of saying is, let's answer that question. Let's go back and take a look. So the limit as we go to the right. So if we approach, in this case, we can't approach it from the left. It's not defined there. We can approach it from the right. And the limit clearly, as we go from here, is toward negative 5. It goes to 0. Okay, so the limit is to go to negative 5 from the right is equal to 0. What that tells us then, so is continuous from the right. So our left endpoint is included because it's continuous from the right. The limit as we go toward the right is the same. So let's darken that in. That's now a darkened circle. We can say that now because the function exists there. Okay, so the limit is the same as the function value at that endpoint, so the endpoint's included. So the same thing for the other endpoint. As you'll see, it's worked basically the same way. So we're going to plug in x equals 5. We do that, f of 5, and we're going to get the same result as we see, so 25 minus 5 squared. And that's going to be the square root of 25 minus 25. to the square root of 0, which is 0, okay? So f of 5 is equal to 0. And think about the limit. Let's go back at our function. In this case, I have to approach it, can't approach it from the right. It's outside. I approach it from the left. As we approach 5 from the left, our function, the y value, what does the y value do? It goes to 0. So the limit as x goes to 5 from the left of f of x is also equal to 0. So this function is continuous from the right, from the left. I get those backwards sometimes. From the left, say the wrong thing. Okay, so that tells us that our right endpoint is included. So f of x is continuous on the interval. So before we said it was definitely continuous on the interval from -5 to 5, not including the endpoints, but we had to check the endpoints. And since we did, we know this endpoint exists and it's right there. Then, so fx is continuous on the interval from -5 to +5 with endpoints included. Now, it's kind of a lot of work just to show that. You kind of basically tell it from the graph, but you want to make sure that was clear. Okay, so the way to actually show it is that way. So basically, graph it, figure out where it's continuous. The basic function is continuous, and look at the endpoints. And once again, depending on which side of the function you're on, you have to approach the endpoints from where the function exists, not outside of where the function doesn't exist. So in this case, in this side, the left endpoint is from the right endpoint is from the left, and both those were the same as the function values, so the endpoints are included. So now say it's continuous on that interval here. Okay. Now, the last topic I want to talk about is what's called the intermediate value theorem. Okay. And the intermediate value theorem, let's take a look at it. Let's read it first. Let's make some sense of it. What it says, the function f is continuous on some interval a and b, the endpoints included, and L is some number between, but not equal to f of A and f of B. The function values, the y values that were A or X and for A and B. So it's between those, not those. Then there's at least some number C in the interval between A and B so that f of C is equal to L. That's kind of mathematical language. It may not make a lot of sense what it's saying, though. It says, in other words, since f is continuous and L is some number between f of A and f of B, the function values of A and B, then the function has to equal L somewhere in there since it's continuous. So let's take a look at that over here. So let's just draw a basic function. So here is A, and here is B. And let's say my function looks like this time. This is f of x, okay? This point right here, this, of course, is f of B. And this point right here, this is f of A, okay? So what this says, since this function is continuous in between these points, okay? And what this says is basically I go through every value from f of, in this case, downward, f of A to f of B. Okay, I have to go through every value. So if there's some point L here in between those two that exists, that means there has to be some C in between. If you plug C in there, it gives me L. Okay, it's just a way of saying if I go through every Y value between f of A and f of B, and L is some number between those, and some value in between A and B that has to give me that as an output. That's what that means. Okay, so let's look at a quick example of that. This will be our last example for the day. And let's call this number 1. So let's see, what should I, actually I need to, think just a moment. Let's just do a really basic example. Okay, let's do f of x. Let's do a linear function. F of x is equal to 2x on the interval of on interval from 1 to 10. Okay, it's just a really basic function. It's a linear function. Okay, so it's a fairly steep function. It's kind of like this. All right, so here, let's say this is where it's 1 and 10. And so if you plug in 1, okay, f of 1 is going to be 2. F of 10, plug in 10 for x, is going to be 20. Okay, now pick any number between 2 and 20. Okay, so I can ask the question is, let's say, y equals 14, an output of f of x. In other words, there's some function value. It's going to be a function value of output. There's some x I can plug in. It's going to be a function value of 14. Okay. Well, clearly, so the answer is yes. It has to be, since this is a continuous function, because 14 is between 2 and 20. Okay. And f is continuous. So f goes through every y value between 2 and 20. Okay. So basically what this means is it's a continuous function. And my lowest for by A, my lowest x value is input is output is 2. The highest one is 20. I know I have to go through every single value between 2 and 20. Okay. So there is some function value, if this is 14, okay, that's going to give me, let's call that C, is going to give me that. Now, in this case, it's easy to find out it's going to be 7. But if you had a more complicated function, it might not be easy to find the value, but you know it is. You know that's true. You know, since it's continuous, it has to go through that. Now, if it wasn't continuous, if I had a hole in the graph or a jump discontinuity or something like that, that wouldn't necessarily be the case. In this case, I know that's true because it's continuous. That's what the intermediate value theorem tells us, is that there has to be some input I can use in between A and B to give me 14. Okay, let's briefly review what we've learned so far today. So we learned the definition of continuity at a point. And basically means if the function exists there and the limit is equal to that value, then the function is continuous at a point. We learned how to check for continuity with our checklist. We learned three main types of discontinuities. We also talked about, we didn't talk much about the rules, but those are useful rules to know. Learn about what it means for something to be continuous on an interval, and learn about the intermediate value theorem. It guarantees we have function values if a function is continuous. Thank you. Have a good day.